Hi, my name is Heather Welch. I'm with NOAA and University of California, Santa Cruz, and today I'm presenting Aligning Management to the Spatio-Temporal Scales of Fisheries Non-Target Species Interactions. By interaction, I mean any unwanted encounter between a fishery and a non-target species. So this is a species they're not trying to catch. And by spatio-temporal scale, I mean how do patterns of interactions vary across space and time. So for example, if we have a crab pot fishery that's targeting crabs, and it has unwanted interactions with humpback whales, these are the non-target species. The spatio-temporal scale of these interactions might look something like this. As the whales migrate north from their winter breeding grounds, they overlap with the fishery and have unwanted interactions, and this happens again on their southward migration. In order to align management to this spatio-temporal scale, we need a management area that is spatially fixed and temporally seasonal, because the interaction we're dealing with is also spatially fixed and temporally seasonal. So that might look like this. As the whales migrate north and overlap with the fishery, a management area comes into effect, and this happens again on the southward migration. So we're avoiding interactions using a seasonal management area. Now, the characteristics of these interactions can vary greatly depending on the characteristics of the fishery, the target species, and the non-target species. So in another example, if our fishery is a swordfish fishing fleet, which targets swordfish and has unwanted interactions with blue sharks, these three features are highly mobile, and therefore we can expect their interactions are going to be highly dynamic in space and time, and therefore we will also need a management area that is highly dynamic in space and time. So this management area is coming into effect when the fishery in white overlaps with the non-target species there in blue. Today I'm going to be addressing three questions. First, how do we estimate the spatio-temporal scales of interactions? Secondly, how do we use estimated interactions to evaluate current management strategies? And last, how do we use estimated interactions to inform future management? Or how do we align management to the spatio-temporal scales of interactions? And I'm going to be addressing these three questions through the lens of two case studies. In order to estimate the spatio-temporal scales of interactions, so this is question one, we need two key pieces of information. First, we need to understand the location of the non-target species, and second, we need to understand the location of the fishery. Then we can intersect these two pieces of information to find areas of overlap, and for each area of overlap, we need to calculate interaction risk. So this is the likelihood that an interaction actually occurred within an area of overlap. It's some sort of measure of uncertainty. Thus far, we've addressed spatial scale, so we are talking about locations and areas. In order to move to a spatio-temporal scale, we need this information across a time series. So we need to understand how interaction risk, which is inherently spatial, varies across time. The study is Australia's eastern tuna and billfish fishery. So this is a long-lining fishery that operates in the area in gray that you see on the map, and it targets tuna and billfish. This fishery has unwanted interactions with a number of species, but the ones I'm going to focus on here are 7 of its most commonly caught shark species, so that's going to be 7 non-target species. Moving to the flowchart, in order to estimate the location of the non-target species, we calculated their habitat suitability using Maxent. And to estimate the location of the fishery, we acquired effort data and converted it into number of hooks per pixel. In this case study, interaction risk is a function of habitat suitability times effort, so that is habitat suitability for the non-target species times fisheries effort. And to move to a spatio-temporal scale, we calculated this for each month between 1998 and 2008, so that's 120 months in total. I think any sort of time series data is easiest to see as an animation. So here we are going to have a monthly animation of interaction risk. Again, that's habitat suitability times effort. and interaction risk ranges from high in red to low in blue, and you are seeing 120 months here. Question 2, how do we use estimated interactions to evaluate current management strategies? Here is current management within the study area. It's called the Commonwealth Marine Reserve Network. And in the panel on the left, we have the original 2012 network configuration. And then in 2015, it was rezoned, and we see that configuration on the right. So in order to evaluate the efficacy of these two configurations, we asked, if these reserve networks had been in place during our analysis time series, what proportion of historical interactions would have been avoided? Here on the y-axis, we have the projected percent of interactions avoided by the reserve networks, and we have our 2012 and 2015 reserve network configurations in gray and green respectively. So across the board, at any given point in time, less than 15% of historical interactions would have been avoided. So we would say that neither of these two configurations is that effective at avoiding fishery non-target species interactions. And if any of you saw the news last week in late July, the Australian government has released a new proposal for the reserve network plan, and we can expect these numbers to get even worse. They've devoted significantly less area to no-take areas, unfortunately. Moving back to question 1 and on to the second case study, which is the U.S. drift gillnet fishery. This is a drift gillnet fishery that targets swordfish and operates in the area in gray that you see on the map. And this fishery has unwanted interactions with 3 non-target species. So we have the California sea lion, the leatherback sea turtle, and the blue shark. So moving back to the flow chart, to estimate the locations of the non-target species, we calculated habitat suitability using boosted regression trees, or BRTs. And we took a different approach to estimate the location of the fishery from the last case study. We calculated the habitat suitability for swordfish, again using boosted trees. The logic here being that the location of the fishery is going to be correlated with the location of its target species. In this example, interaction risk is the ratio of non-target to target catch probability. In other words, this is the ratio of habitat suitability for non-target species to habitat suitability for target species. And we calculated this for each day in 2012 and 2015. So here we have interaction risk as an animation. Again, interaction risk ranges from high in red to low in blue. And in this example, interaction risk is the ratio of non-target to target catch probability. And you're seeing each day in 2012 and 2015. Question 2, how do we use this information to evaluate current management? Here's current management in the study area. It's called the Pacific Leatherback Conservation Area, or the PLCA, and it completely prohibits the fishery from operating within its boundaries. As you can see, it's quite a large area. It covers over a third of the western U.S. EEZ. And so to evaluate its efficacy, we said, if we switch to a dynamic closure, so this is a closure whose boundaries are flexible in space and time, can we avoid the same amount of interactions? In other words, can we become more efficient in terms of area without losing efficiency in terms of interaction avoidance by moving to a dynamic closure? And we can. So here on the y-axis, we have the percent of the PLCA area required to avoid the same amount of interactions. And we have our 2015 and 2012 analysis years in green and gray, respectively. So across the board, it would require 25% of the PLCA area to avoid the same amount of interactions if we switch to a dynamic closure, which is what we've done. So this is that last question. How do we take the information on interactions and use it to inform future management? And this is a schematic for what we are calling EcoCast, which is a tool for maximizing target catch and minimizing non-target catch in real time, so at the daily time step. And I'm not going to walk through the whole schematic, but I'll draw your attention to the right-hand side, and I'm going to briefly touch on the EcoCast product and the EcoCast tool, which are our 2 main outputs. The EcoCast product is hosted online on an FTP site, and it's updated every day. And if we click on one of these links, we get a daily map of interaction risk. And we're going to disseminate this each morning to the fishery that we're working with. Our EcoCast tool is an R-Shiny web application in which managers can explore the impacts of different management scenarios on the EcoCast product. We're going to be rolling out both of these things this month in August, so we're actually going to roll it out on the ground, or I guess I should say on the water. So please stay tuned to see how this project unfolds. Thank you very much.